Uh, shall I start, sir?
Yes, Nishan.
Good morning to one and all present here. I welcome you all to the final day of 1 week workshop on statistical techniques for data analysis. Today we have with us Professor Gagan Mohanty from Tata Institute of Fundamental Research. His research theme revolves around the fundamental questions like what are the basic building blocks of matter, and starting from there, how did we one end up at the present state of the universe? Professor Mohanty studied BSc with Physics Honours and MSc from Utkal University, Bhubaneswar, and then joined TIFR Mumbai as a Ph.D. research scholar in 1996. Sir is also a recipient of many awards and scholarships like postdoctoral fellowship from Particle Physics and Astronomy Research Council UK, Center of Excellence position in Bell, Japan, Kanwal Rekhi Fellowship for Career Development at TIFR Mumbai, and many others. Professor Mohanty has been a part of L3 experiment at CERN during his PhD, B bar experiment at SLAC during postdoctorate. Currently, he is very actively involved in Bell second experiment, not only as a researcher but also as a leading a team of researchers across different Indian institutes. Along with this, he is also the coordinator of physics analysis at Bell. He is also an active member of CMS collaboration at CERN, working both on analysis and detector development. He has delivered various talks on B meson physics and CP violation. Sir has many publications in the reputed national and international journals. He keeps a very keen interest in teaching and is always available to share with others the ever-growing excitement for his field. I welcome you, sir, on behalf of Department of Physics, NIT Jalandhar. Now, I invite Professor Mohanty to deliver his talk for the day.
Thank you, Nisa, for this kind word. And I'm sorry for a little late. There was a meeting, and I requested Sunil to move by a few minutes. So basically, the title of the talk, as I don't know if you have said, I gave a pretty sounding very easy job, easy title. That how do we, like, you have a box full of black and blue and red boxes, and how do you separate them? In a classical storm, as you can see, it is very easy, and the fact that decides that distinguishes these two kinds of boxes, these two type of balls, I'm sorry, is color, right? One is red and other one is blue, and we just use that. And at the end of the day, you have 100%, like, you have 100% accuracy, or what we call efficiency. That there is no way, if you are, I mean, with all due respect, if some of you are color blind, if you are not color blind, you know what is blue and what is red. You will be 100% efficient in distinguishing that, that the one color going into one side and other color going into other side. um, Excuse me, that was my phone. So going from that to the modern science, especially data science. I'm busy in a meeting. I'll call you later. Okay. So, going into the data science, keeping the context of this workshop in mind, what I wanted to sort of say, the actual thing that in high energy physics experiment, we have very, very complex data. And in the complex data, we are quite frequently have to face the problem that where you want to separate different kind of particles. Of course, this is something particularly for the young student. When we say something electron or something muon or something pion, something proton, I mean, it is not like the blue box, red box in that sense that you can sort of see by eye or something like that, but you have a very well developed instrument, sort of super microscope, namely the experiment, which goes down to that level of 10 to the power minus 18 meter. Basically, for each of the particle, they have certain properties, and through that properties, the difference in the property, these particles interact with the detector medium and they give the signal. So we get, at the end of the day, we get the signal, and looking at the difference in the signal, we try to discriminate one set of particle from the other. And that's the crux of the problem for today. And I wanted to give this title. So let me just start sharing my screen, and for that, what do I do? More action. One second. How do I share my screen?
Sir, next to the unmute option, there is an option share, open share tray.
Right. Yes. Sorry. Yes. Open system preference. I should have done this earlier. So I have to go to, where do I go? So in Mac, I go to notification. I should have done this earlier. I usually use Zoom, so that is why okay. Microsoft allow notification. Okay, fine. So that sounds okay. Yeah. So can you see my screen? No.
Not yet, sir.
Not yet. Why I am not getting them? Open share screen. More action. So device setting. Don't know. It apparently took me somewhere. I have to keep the setting.
Sir, no, it's just by clicking on open share tray and then
Yeah.
get
So
option.
when I do that now, it doesn't give me any further option. Just open tray, and now it is saying open and share. That is open share tray, close share tray. That's the only option I see. I don't know. Sorry.
So some option will be there.
Your desktop screen or something like that option is not coming. No.
Is it possible from your side, kind of a small demo or something? Otherwise, I can continuously speak, and but the problem is, if you want to see my slide, that will not be possible.
Nisha, can you share and tell exactly?
Yes.
How?
Yes, ma'am. Yes, ma'am. I'll
share your screen and.
Okay. Okay. Let me send a link probably to Nisha so that she can share, and probably maybe Professor Gang can try simultaneously the things on his Mac, right? So I have got some instructions. Let me share that to Nisha.
Okay. Can you see my screen, sir, now?
Yeah, I see your screen with my picture.
Yeah. So, sir, this option, no, this sharing option.
Right.
So, yeah,
So
when you click on this, like
I have. So what I see the first one button which says Dr. Arvind Kumar started recording. That is the recording window. Then I see turn camera of the video. Then mute option, the audio option. Then this close share tray it says, and if I click on that, it says open share tray, close share tray. So presumably I have to go to my setting and something I have to do. But that I thought I went to the that permission that I have already granted in the for this Microsoft thing. So I
Maybe
don't
you
get.
can send your slides to Sunil and he can share.
Okay.
Yeah,
Sunil, is it
That
okay?
may be better. Okay. Thanks. So
yeah.
just. Mhm.
Sunil, that will be okay, sir. Please send me that. Because these instructions, Nisha, you are using Windows and sir is using MacBook, so the instructions are little different for Mac. That's the I was saying. I have found out those instructions, but that's going to take
Yes,
little
sir.
long.
Yeah, I think best is I send you the slide, and but then you will be once you put like okay. Let me first send then before. Okay, so okay, Sunil, I sent to your NITJ.ac.in. So it's the message is sent from my side,
Okay, let
and
me check.
we go to slide number basically 4. All right. So while Sunil is getting that thing, let us continue discussing. So as I was saying that this example of blue and black, blue and red balls inside the box versus you have a huge data sample where you have different type of particle, and so you have two problem in hand. One problem is you want to distinguish different type of particle based on the difference in their signal. I mean the how they interact inside the detector medium. And then other problem you have that in event by event you want to distinguish a class of event from B class of event, and in each of these class of event again we have different final state particle making that class of event. To give you a concrete example, if we pick up I'm sure all of you at least would have heard of let's say the Higgs particle being discovered by the CMS and Atlas experiment at CERN. Now this Higgs particle was discovered in two final state for the first time, where like Higgs decay to two photon. You know our electrically neutral particle, the photon. Messenger of the electromagnetic interaction. So this Higgs decaying to two photon, or the Higgs going into the final state of four charged lepton, namely electron or muon in this particular case. Now, the point here is that you can get the same final state, like you may have two photon or like four charged lepton coming from various sources. And now question is, your job is to kind of figure out the actual signal coming due to the Higgs particle going into this final state. Now question is, you have what we call background, so that the signal is your Higgs decaying to this final state, and you have different background also giving to the same final state. In your detector you directly don't see Higgs as Higgs. What you see, you get signal due to this stable particle, because Higgs is very unstable particle. As soon as it is produced it decays. In your detector you have signal due to either the photon and by the charged electron, like namely electron and the muon. So yes, Sunil, have you got this email?
Yes,
Yes,
it has been
I
received.
got the. This is Arvind. I am sharing the slide. Just a minute.
Okay. So the point here is that you have the final state to be same between the signal and the background, and you want to given the difference in the characteristic, like your Higgs decaying to two photon has certain characteristic. For example, most important characteristic, like so you go to the fourth slide. A series of one of my collaborators, and just to because I will be following his slide, so I'm happy to use his slide, but the idea will be discussed as we proceed. Yeah.
Let me mute myself actually, otherwise there will be echo problem. Just a minute, sir, please.
Okay. Okay. Yes. Yes. So you can see the slide. So the idea, as I said, that how do we classify a given set of events? How do we kind of tax an event as, let's say, Higgs going to two photon versus the two photon coming from some kind of it is not actually a decay, it is something else. Let's say just two photon being produced inside when proton being collided at LSC, the two photon are coming from they're unrelated. They don't come from a particular decay final state, from a decay of a particle. So that is what we want to do, like the way we said in the classical sense of the two color ball of blue versus red. You use color as a feature to distinguish one class of balls from the another class of ball. The life is not so simple in the elementary particle physics. So here you not only have one feature, you have number of feature. So sometimes we will say feature as variable, we'll call it input variable. So this feature, each of the feature, they bring in certain discrimination power into separate to kind of distinguish these two set of two, or it could be multiple set of event, multiple set of processes. And so that is what we want to do, what we call multivariate analysis. So there are several ways this thing is done. So if you go to the next slide. Um, so, so what we want inside your data, like the way inside the box you have several number of balls. So inside your data sample you have several interesting events. Okay, and each of the event, they have got certain kind of feature or certain kind of characteristic, and that is what you want to exploit. Now, so let's say I want to discriminate two class of events, class A versus class B. Unlike in the case of two classes of balls, there is no overlapping. Blue and red, they will never overlap. I said unless you are colorblind, for you it is clear distinction. In this case, what you will see that it is practically sort of we don't have that kind of situation where the A class of event is completely disjoint from the B class of event. I assume all of you are familiar with the set theory, and the fact is the total class of event, the total data sample, let's call it U. Within that you have multiple subsamples. So A is belongs to U and B also belongs to U. What you have interestingly, that A intersection B is not zero. I mean, there is some overlapping. Despite your best effort, you are not able to completely discriminate A versus B. I mean, that is not like 100% separation power that you can exploit to separate A from B. So if you go to the next slide. So you have this different feature, as I said, for each event. All right, like the way for the two ball, you have the color is one feature. Here there is only one feature, but you can add it, like make the one is sort of spherical ball, other one you can make it like if you play Ludo, like the square. I'm sorry, the polygon, right? Or you can have different kind of shapes for the ball. So you can have the feature like color, then shape, so on and so forth. You can keep on adding. In this case, also there different feature. You have n feature. We exploit that n feature to determine. In the case of ball, you have there is kind of 100% separation. In the case of particle experiment, the data we have, you don't make it 100% this is Higgs signal or 100% this is the background. What you have, event by event, there is a Higgs likeness or background likeness. So we need to determine, or we need to actually, based on this different feature variable, we want to calculate the probability that a given event, how much it is like a event and how much it is like a B event. If it is a matter of A versus B, so sort of when you are talking of binary classification scheme, so you know the probability of this event belonging to A. Of course, the very simple thing that I'm sure from the previous few lectures you would have already seen, that probability always lies, less than, the probability cannot be greater than 1. So it is always less than equal to 1. Now the complement of the event belonging to A is actually the probability of the event belonging to the B. I mean, that is what you have, the two classes of event. So what you do, you exploit this feature variable in certain way to find out the eventness, the A-ness and the B-ness of a given event. So if we go to the next slide. So here you see on this some kind of distribution of so this is the U, if you remember, that's the total event A into B, and here what you see, there are two, this is a kind of a scatter plot, what we call, so it's basically the distribution of this A type of events which are more likely A type, represented by the red dots, and the events which are more like B type, represented by the blue dots. And it is shown in the x-axis and y-axis. There are two feature variable, and in each of the feature variable, if you project the data, then you find this one-dimensional histogram. I'm sure all of you. Is there a question? I see there's some background noise.
I request all the participants to please mute them,
please
because this is causing
you have a question,
interruption in the talk.
Otherwise, I'll think that there is a question. So anyway.
Yeah. So please. Yeah, it's okay, sir. Now.
All right. So what you see here. So Nisa, maybe you, time to time, if there is a way people can raise their hand, or if there is a comment they have, if you can pause me and let me know, then that will be nice. Otherwise, it will be a little bit difficult for me to sort of see that if there is some question in between. If there is some mechanism, please try to see that.
Actually, sir, questions are being requested at the end of the talk, so that you are not interrupted in mid.
In that case, I would request everyone to mute, please. Otherwise, I get a little bit thinking that someone trying to say something. Okay. So here you see the distribution projected into the two dimension, what we call, or two axes, and you see that there is a clear-cut separation. There is some not 100% separation. You see that the blue distribution and the red distribution, there is some overlap region, and that's what we are saying, that A intersection B is never going to be 0. And what you see in both the cases you have, and the idea is that can I optimally, of course you have the option of sort of simple and straightforward option, what we call cut and count analysis method. So you can apply some selection criteria if your job is to select a red as opposed to the blue. You can say that in this distribution x1, or let's call it x and y, which is projected into x-axis, that's x variable, which is projected to y, let's say that is the y variable. So if you want to select the red, for example, you will say that x should be less than that x threshold or x mean, and y should be less than the y minimum. Conversely, if you want to select the blue, you will take x greater than that threshold value and y greater than that threshold value. Now question is, each time you apply this selection criteria, you will lose some part of the signal, and in your selected sample you will also get certain kind of background event. So now I'm going back to the Higgs going to gamma gamma, Higgs going to 2 photon versus the signal, that is the signal versus that 2 photon coming from some standard model, other kind of standard model processes, like just 2 photon coming from the jet. So you will always have some contamination. Now question is, can I combine this information together? How efficiently I can combine this information into a single variable, and that may give a much better separation between A and B. So that's the job, and if we go to the next slide, that's the job where you want to exploit the multivariate analysis method. And so there are certain algorithm, there is certain way. So the how are we going to combine information coming from the different type of information, different type of feature, going back to our classical problem, color, shape, size, nature of the solid, so various feature that you want to exploit. Similarly, you want to exploit different feature of your input variable, and that you want to combine. So the way we combine will decide, the algorithm will decide how we combine, and whether that algorithm is a good algorithm and optimal algorithm for us. There are certain way to quantify that, and there are a couple of things I should say, that there is no unique method. There is not a unique method that the algorithm or the technique that work from person A will work on person B, because each problem is unique and each problem needs to be handled in its unique manner. So you have to kind of before doing the data analysis, you have to keep in mind that what is the level, given the data sample size you have, the kind of complexity you have, what is the ultimate statistical precision that you want to achieve, and what you want to do basically. So there should be some understanding that what is your experimental sensitivity. Now, in order to achieve that kind of sensitivity, the next stage would be that which algorithm, which method, sort of combining this feature in different way. There are several ways we can combine. Then we need to understand which is the best algorithm, the most optimal algorithm we have in front of us that can allow us to combine this feature and try to understand giving the best possible performance, best possible sensitivity. So of course you have to do lots of things, like how exactly we have to do, and how we will compare these various feature, various algorithm, that if you have to make a choice that which one I should go at the end of the day. And of course as an end user, sometimes for example there are lots of available algorithm, there's lots of toolkit, lots of software package are available, and things are evolving, because right now this data science and particularly this machine learning method is really like evolving area, and it has mostly came from the computer science, but in high energy physics experiment and theory also, we are sort of getting more and more over the time and getting into more and more complex analysis. That's because that the complexity of our data has gone manifold. For example, like kind of Nisha said, made a remark that when I did my PhD from L3 experiment, like right now this let's say CMS and L2 experiment, the degree of complexity I could see has evolved tremendously, and that need to be handled at the level of analysis. So going to the next slide. So, as I said already, there is not a single right answer to a given question. it has to be problem specific, that you need to have a clear understanding that what is the problem you want to solve and make a balanced decision. And the very simple thing, the rule of the thumb is that you should, try to keep things simple as possible. All right. So it is like if you want to do a task, whether I need a simple needle or I need a big drill machine. So the thing is, if I can get the job done with a simple needle, why should I get into the drill machine? So the simple idea is always start in a simple way and then sort of slowly build up the complexity, because in the process of building in the complexity you will have thorough understanding. Don't start from the top and then you get down. It's rather bottom to top approach. Okay, next. Yes, so first is this very simple way of you have given set of feature variable and you want to apply certain criteria. So that's what we call caught. It's not really caught in that sense. It's just like applying. You have sort of different feature variable and you want to apply very certain criteria on that. So please next. So so given this feature variable, input variable, so you want to have, okay, if this condition satisfies this, if not other. So it is a kind of step function, as you know that the step function is 1 if the x is greater than that, 0 otherwise. Similarly, if in this particular feature variable, input variable, if I satisfy this condition, that is selected or rejected. And you can have n such variable, so that is like n dimensional step function. Okay, and at the end of the day, so you'll say, well, how do I decide where do I put the boundary of my step function? Where do I decide that where do I apply the selection cut? And that has to be, so physics is very quantitative. We do things in a very, there's a figure of merit. There is a certain way we do things. There is not like ad hoc and very arbitrary way of doing things. So in this particular experiment, largely speaking, we go for, when we are doing the optimization, that where do we really apply the selection criteria? We do some optimization and the parameter we take largely is so-called signal significance, and it is given as the number of signal that you select by your selection criteria divided by the square root of the sum of the signal plus background. That is the expected statistical uncertainty. So at the end of the day, it's a relative expected statistical uncertainty, the sensitivity that you want to achieve and that you want to have got the best possible value. So go to the next slide, please. Now that's the one way of, and the simplest way of the doing the thing. So like the way I said, you don't jump into straight to the most complex thing, you go step by step. So if I were to do an analysis like the Higgs example I gave, there is, of course, it is a multidimensional, sort of what we call BDT, boosted decision tree, or there is a deep neural network sort of multivariate analysis technique, machine learning technique, but also we do that cross check or cross validation with a very simple cut and count method, although that will not have the sensitivity that you desire, but at least to understand, you can check these things are going properly or not, going in the right direction or not, because all these method going beyond the simple cut and count method, they're complex, but we should not use them as a black box. We should try to understand that whatever thing we are getting the improvement, that is along the expected line. So the next method we have, that where you want to combine the feature variable called Fischer linear discriminant method. So here you have, let's say, this n number of feature variable, and you want to combine them in a linear method. Very simple. So that so here you have j, the dummy index j, which is going from 1 to n. That is the feature. I'm sorry. That is the number of event you have. So and I here denotes the ith event. 1 second, I'm sorry. Yeah, I is the ith event, J is the feature. I'm sorry. Yeah, this is the other way around. So the index I correspond to the event you want to talk about. There may be several events in your data sample that you have. So I pick up one event, and for that event, I want to look at the different feature variable, that is J, and then you have n such feature variable, and I want to combine that through a linear transformation, linear method. So therefore alpha j is that linear coefficient, and then beta is certain kind of you can say bias factor that added, and it's arbitrary, and you can set it to 0 if you wish. Now question is, you'll say what exactly I did is a simple thing. Earlier I put a chord, let's say in I apply certain criteria, and I decided whether this way or that way. Now you want to combine them, but how do I gain a better sensitivity compared to the other one? So this alpha at the parameter x you cannot tamper with. That is your data, right? So you cannot do much better than what your experiment entitle you to do. So that is kind of decided by your detector sensitivity. The best you can do is like how optimally you want to combine. So X part remains sacrosanct to you. This alpha is the parameter that you want to optimize on. So how do you optimize that? Next slide. Right, so this is what you see in the bottom two plot, bottom two expression. I don't want to get into the mathematical detail. So basically, if you think of that, the two cases I showed in the few slides before, that there's a projection I was doing in the x-axis and y-axis. You saw there is a two curve, red and blue distribution, and so what you want, if I want to discriminate these two distribution optimally, I want the red and blue to be as separate as they can be. So that means I wanted their mean of the distribution, the peak of the distribution, they should be maximally separated. Not only that, the variance, the spread of the distribution should be as small as they could be. Right, so two things I want to achieve. I want to achieve the mean separation to be as maximum as possible. The spread of the distribution should be as minimum as possible. All right, so therefore, given this expression of y given by the sum upon this j, that feature variable and alpha j xij, I want to optimize on alpha j. So given this expression, I have to calculate that for the OI, the output I am getting, how this the mean distribution would look like, and the variance, the width of the distribution would look like. And that is expression mathematically given in this alpha transpose and x. So x is a vector here, alpha t is kind of matrix way you can given it. So somehow I don't see the bottom part of the slide. Can that be taken care of, because I see it is cutting somewhere, that may be anyway. So going to the next slide. Yes, so this is how we want to combine, and what you see that J alpha, that is the kind of, when we are doing the cotton count analysis, simple cotton count analysis, there we said some kind of figure of merit signal sensitivity. Here, this multidimensional analysis, Fischer discriminant analysis, you have combined everything linearly, and you want to parameterize, you want to optimize on alpha. And the way I want to say, there's a two component hypothesis, event here. We have S and B, signal and background. I want to see the mean separation between them should be maximum, therefore the difference, and we take the square because it could be both positive and negative. All right, so therefore we take the square of that so that it is positive definite always. That goes to the numerator because that you want to maximize on. And the sigma, and I'm sure from the previous few lectures you would have heard, you would have learned about the error propagation, and it's always added in quadrature. So the variance, the effective variance is the signal plus background, that square. And so I don't want to get into the technical, the mathematical detail, and given the expression, the linear way you add them together, J alpha is what you will get in, and that you want to optimize with respect to alpha. So go to the next slide, please. It will be basically d J alpha upon the alpha for each of the alpha, right? So this is n-dimensional optimization. The Fischer discriminant method, depending on how many input variable you have, it is optimizing in that dimension that for each of the input variable or feature, you want to optimally combine so that the alpha for that corresponding variable is optimally combined. So therefore, the dj alpha for that alpha, for each of the alpha, it has to be optimized. Okay, so this is like a global minima, finding out a global minima in a multi-dimensional, in an n-dimensional optimization method. Okay, and once you do that, so how do you do that? I mean, so you'll argue that how do I do this? So this is where what we call the we call it supervised learning method. So, before looking into the data, right, in the LSC data, how do I know this is Higgs going to 2 photon or this 2 photon coming from a other standard model processes? They are uncorrelated. They are not coming from a decay of a parent particle. How do I know that? So we rely on Monte Carlo method, where in theory we know if Higgs decays to 2 photon, this is the way it should come. The kinematics, that is the dynamics, and that the theoretical distribution, they have to go through the detector. So we do detector simulation. Finally, we get sample of Monte Carlo event, what we call Monte Carlo, simulated Monte Carlo event, to mimic the Higgs to 2 photon or signal event, and similarly we get the background event. Given this background event, I know what is expected of signal feature and what is expected of the background feature. I have to train, and in the process I get this alpha. Let's say if I'm going a Fischer discriminant analysis, that we do, and then you have to validate this. So go to the next slide. Yes, and then you validate, and so basically you see the same thing that we saw previously, that while I was showing that 2-dimensional scatter plot, and then we took the projection and we got the the red versus blue two kind of thing. So here what you see that you have two variables, okay, and these two variables are optimally combined through Fischer discriminant method, a linear method, to give eventually a separation that you achieve. And you see what you see the individual level. If you see the overlapping region in any of the two, on the left hand side you have two plot on top and bottom, and right hand side you have just one plot. One thing you can easily sort of convince yourself that the overlapping region between the red and the blue, that the area under that overlapping region has reduced, and that's the technique that we want to see. Okay, so now let's move on to the next slide. Okay, and yeah, I think we can probably skip this slide. All right, no, I'm sorry, go back, I'm sorry. Yeah, so now there are certain things like where, let's say, this linear discriminant method will not work for you. See, the assumption here that this feature variable, we say, they are not completely uncorrelated. What I mean by that correlation, the information content that you have in this feature variable, pick up any of them, is not completely independent of the information contained in some other feature variable. All right, so there is certain correlation, however small that may be, or it could be large also. Now, this nature of correlation, there could be linear or non-linear. If it is a linear correlation case, imagine the case x1 and x2 are linearly correlated. So in that case, x2 can be expressed as mx1 plus c. I mean, you all know this standard equation linear relationship, mx plus c. Or mx1 plus c. In that case, when you combine that alpha 1 x1 plus alpha 2 x2, it can continue for alpha and xn. Now I replace x2 by mx1 plus c. Now you can see effectively your dimensionality goes down by 1. So there will be no more x2. But it is still okay. The problem is fine. But the issue will not be so simple. if the correlation becomes non-linear, and that is where Fischer discriminant has the major handicapness, that you cannot use linear discriminant method in a situation. Very likely most of the situation in the high energy physics experiment are linear, so you have to go beyond linear discriminant method, and that's what we take next, and this is called neural network method. All right. So how does the neural network works? As you just see the first part, neural derived from the word neuron, like the way our brain operates. So if you go to the next slide. Right. And there is lots of interconnectedness, and there is a central processing unit well within, well secured with our hair over here, and that anything, some mosquito bites at certain part of your body, and you might be reading a book, and without looking at that side your hand immediately go and bangs on the mosquito. And the way it operates, because that when the mosquito bites you, that particular part of your body, the neuron gets activated, and then the information flows to the central processing unit. Central processing unit instructs your hand, check the necessary action, and it's pretty much on target, that where the mosquito is there. Similarly, we have the input feature variable. There are n inputs, and that we call it impulse, like that is, and then you want to interconnect them. At the end of the day, if it is a binary classification scheme, you want to either select something as signal or background. Of course, it can be more than that. So you need to interconnect this feature variable. And once I interconnect, so let's go to the next slide. Right. So that interconnectedness is achieved through this weight factor that that W you have, and then again B is some kind of bias term that is added, and you can sometimes ignore it. So and if I go to next slide, probably there is a figure I wanted to see. Can you go further? Yes, I'm sorry. So I will go back maybe the previous slide, but I just want to say this. No. Stay here. So thank you. So what you see, you saw the way that how your neuron in the human body are distributed. So what you see here also, there is input feature variables are being fed into this interconnected network. That's the second word, network, coming into play. And what you see that that from each node, each point, you have interconnected going across. All right. So think of there is a sort of one hidden layer, and so the hidden layer has the number of node as close as it can be to the input number of node you have, and then you see from each of the input node there is interconnection. Each of the interconnection is represented by W, the weight factor, and again, this weight factor is what you have to optimize on. Now you think of you have this picture in front of you. Now you visualize the Fischer discriminant method. What you have in a Fischer discriminant method? You have X variable, and there is one output. The interconnectedness from each input variable to that output is just alpha, right? It's a linear thing. So you have n variable and one output, and there is one connection is alpha. Between these input, you saw there is no way that interconnection exists. So therefore, the Fischer is not able to handle nonlinear correlation. Now, when you allow this interconnectionness, the node in the output gets information not from one unique input node, they are getting input from each of the nodes. So you are intermingling, so you are interconnecting the information, and in this process you are able to take care of the nonlinear correlation. And that's the beauty of the neural network. Now, how we will get this weight factor? You go to the previous slide. Sorry, that activation function it is called. So how you want to combine this layer of input variable or perceptron to obtain this refined separation between two classes of event. So we use some kind of step function that is we don't use step function. I mean something close to step function. We call it a sigmoid function. Largely we use a sigmoid function. So at the end of the day, you wanted something like a wij xj kind of thing, and here we use this y given by this sigmoid function 1 by this 1 plus the expression given there. And yes, and then there are some other option. Now you might argue that why we have multiple option, 4 option given here. I mean, is there a way I can optimize on? Do I have some kind of judicious way, or do I have a sort of quantifiable metric that can say that this is better than that? Yes, you can optimize on that. Largely, it is found out that sigmoid function is the as close as optimal as it can get to be. All right, so let's move on. Yeah, next one. So how do we now optimize on this? Like the way in the Fischer discriminant method, you optimize on the alpha, like that is the parameter that you want to optimize. That is the only only freedom you have to optimize. You cannot tamper with whatever you have in your data. The X1 stay as sacred, as pristine as possible. Similar thing here also. Now, so you want to optimize, and how we get this W, the weight factor, those interconnected, that is basically allowing the interconnection between different nodes. And for that, we define something called error function. Okay, so and basically you want to classify A versus B. Given a set of weight factor, you want to calculate what is the degree of error in my output classification. Okay, so the error should be as close as it can get to be 0, right? So the output classification is really fully A and fully B type. Of course, you don't get to that. There will be always a distribution. It will never get the Dirac delta distribution A and B are completely separated. That neither you got in Fischer nor you will get in Fischer. Neural network. But the way is we should get better than that. If I don't get better on this, why do I get into the complex? Going back to needle versus the drilling machine. So given this weight factor and you optimize, you want to start with one set of weights, determine the measure of error in the output classification, and now I want to go to reduce it. So given this weight, you slightly tinker with this weight and then see which way your error is changing with respect to the weight. So it's like a feed forward system. All right. If you see your error is going in the wrong direction, you stop. That's not the right way to go. Go to the other direction. Again, an n-dimensional optimization. Here, obviously, it is a much complex optimization than the optimization you had at the Fischer way, where you are adding only the linear way you are adding. Here, you are doing this cross communication between different nodes. Okay, and then you will say that we must, how do we do that? I mean, when do we stop it? This optimization. So you will stop it that as soon as you get that we have got a stable set of weight. We have got that set of weight for which that the whatever error you get in your classification, any further deviation in the weight is not really dealing an appreciable improvement in your result, and that is where we can get to the global minima. So you have to really assure about your global minima, okay, because you may be getting into a local minima and kind of think that, oh well, I have got it. So, but then you have to really ensure that that what you have got is not a local minima, it's really global minima, because it's a n-dimensional optimization. Okay, next slide. Yeah, so this is the error function. It is called that mathematical expression. You see, there is a half factor. and you want to get the target type, signal versus background, that is the target type, and yi is the output of perception, where yi is calculated given the xi, the input factor, input feature you have, and that wij. So tij is what you want to achieve, so that remains as it is. Ya is what you want to determine in the process of adding the x and w's. Okay, and you want to optimize on this epsilon I with respect to what? With respect to the weight, like the way we said there. You want to optimize the separation between the two Fischer output discriminant in a way that numerator you had the difference of the mean squared, denominator you had the summation of the square of the variance, basically the sum of the variance. So yes, now you have to, if you have n event, then you have to totally sum them up. All right. So what you do, this is again what we are saying is supervised learning method. Like the way we said Fischer method, that you know to start with what is A and B in Monte Carlo data, and you do the training. Once the training is done, once the weights are done, you now test your thing in an independent subsample of the data. Okay, without once you get the weight factor, we do not distort it anymore. We do not touch it. Anyway, excise the feature part you don't touch at all. Once your weight are fixed, you get the thing in stable way. You now apply to the independent data set. You must, if the independent data set, let's say, signal type, here you have trained and here you have tested, and background type, whatever output you had got in the training thing, if your method is properly done, if it is not overtrained, if it is not if it is stable, if it is really stable, that your output, what you get in the output signal, the output you get in the test sample for the signal, and the output of the training sample you have for the signal, this should match to a good degree of accuracy, and that will be test. Think of like this: if you have a situation, you have only red ball, there is no blue ball. If you train with such a sample, it's like a biased training, and in that case, you go to the real world where you got red and blue. Your technology, your method will always think of everything is in red, right? Because it is trained in such a system, it's biased to in certain way. So I don't want to get into more technical detail than this required. So at the end of the day, if I want to give a take-home message, that you have certain feature variable, and that is what you want to exploit to classify certain way of event. We started with color and the size for the red and blue ball in a box, and now we're talking of this input distributions having these different the data events having different input distribution or feature distribution, and that you want to exploit in certain way. You want to combine the information in certain way so that you get a one output distribution, and that optimally discriminate A and B, A classes of event from B classes of event. And I showed you in two ways. One is in a linear way, and that works reasonably fine if you have the case where you have a linear correlation or no correlation. It doesn't work if it's a non-linear. You can just do a small mathematics that if you add in non-linear correlation, you can see that easily it will fail. On the other hand, thanks to this interconnectedness of the non-linear method neural network, the way our human body operates, that allows you to take care of this nonlinear correlation, and by optimizing on the W's, you can get the best possible, the best performance as possible. So I would like to stop here. I know in between there is a bit of disruption, but let me see that if there are any questions or comment or any suggestion.
Anyone? Any questions from the audience? I think, sir, no questions.
Okay, So
yes, sir. No, there was one question in the chat window. That just a second. So the question was that if we want to shift to the data analytics, I think I don't know the name of the participant, but he said that if we want to shift to the data analytics, right, and from the physics background, then what are the things they should work on before performing better there?
yeah, so I think this is a good. So the question is, what are the transferable skill that we will get from, let's say, from this, if you are doing some data analysis in high energy physics, that what are the transferable skill to other area? And so yeah, I mean, I think the thing is, the degree of complexity that we deal with the experimental data, the big data we are talking about. You already, I mean, actually, there's lots of people are doing that. I mean, even during my PhD time, also, many people after their PhD, it has not yet so much happened in India, but okay, there's few example I have, but let me first talk about outside. Many people, both in the US and in Europe, they have gone to in the US, particularly people joining Google and various Microsoft and those kind of where you have this big data churning, and in Europe, people have joined similar thing as well as joining the banking industry, particularly prediction, right? So we talked of so far the supervised learning where you know what you are expecting, right? But you can also have unsupervised learning, like when you want to predict the certain things that you are not accustomed to, like given this feature, what can happen, sort of. So that is unsupervised learning method also. That is, getting into some little more complex situation, but that is also possible. I mean, if you so maybe also in high energy physics we deal with unsupervised learning method as well, not so much you do every day now and then, but point is you would have lots of transferable skill, and if you want to sort of move the field to the industry where, let's say, big data analytics are there, from this field you would have enough transferable skill. If that is the question, I think I addressed, or I don't know if I didn't. So whoever asked the question, please let me know that if I address the point.
So probably might the participant has got the answer to his question. There's one more question there that you were mentioning during presentation about the overtraining, and I think contrary, the undertraining should also be there. So the question is that how do we ensure that while applying these techniques we are not going for overtraining or undertraining?
Right.
Also.
Yeah, so the undertraining and overtraining part is very, very important. So how would we ensure that? Is that you need to, so one of the key thing in this multidimensional machine learning method is testing and validation. I had some colleague, they were working they're working in this software industry. So whenever they come out with some product, new product, software product, they have to have a testing team. And so testing team, they're not writing new package. So you can say maybe their job is little less comfort. I mean, less adventurous. Yeah, that may sound so, but it is very, very important to call a product as a successful product. That whatever you you are targeting to achieve, that it should not be only like you have data set here. And so one of the key thing in physics is the reproducibility and repeatability in an experiment. It cannot that you did something in this subset of data, someone else, and you pass out and you go wherever, you maybe in the industry, or you stay in academia, or you might go out of the field somewhere else. But someone else looking at the data 10 years down the time, doing the analysis, same analysis, should not get completely random result which is independent, which is distinct from yours. So in that sense, it is very, very important to have repeatability and reproducibility. And in the process of this overtraining, undertraining, so it is important that while you are doing supervised learning, in this case, for example, you have to ensure that the training is done in some sample. So basically, the thing I didn't say much, this is actually few, because I wanted to finish that, I didn't want to get in too much of detail into that. So you need to make sure you divide the whole sample, the signal or background, let's say, into two independent subset of sample, what we call training and testing sample. You optimize your weight parameter if it is a whatever nonlinear method, or the alpha is the coefficient, linear coefficient in the Fischer method. Once you optimize on this training sample, then you forget about the training sample. You stay them aside. You got a sample which is supposed to, you got a parameter, set of parameter alpha or W, and input input features are all same. I go to an independent subsample, the testing sample, and I don't touch it anymore. But if this was a signal and this was the signal, this was signal training, this was signal testing, this is background training, this is background testing, I apply this thing into this side. In the signal case, whatever output I get, the desired outcome I get, right? If my training is just perfect, neither under nor over, I should get the output which should be matching with the output that I had in the training case, and the same true for the background also. Okay, so if I don't achieve that, that already tells me something about the undertraining, overtraining. Depending on which way the error goes, we call it. Mostly we talk of overtraining. I mean that. So there are certain things you have to make sure. That one rule of the thumb is you should have two independent subset as training and testing. The size of the data that you have in both the cases, they should be fairly equal, similar. I mean, not exactly equal to the level of 1,000, but not like 1,000 versus 100. That will not work out. It has to be similar size in both the case. The other thing also I didn't tell, maybe I should have said, is that you don't do this thing with a very small data sample. You have to get a good number of data sample when you are doing the training. So there is that inherent uncertainty or error that you will get in your classification that will depend on the total data size. So-called the statistical error will depend on the total data sample size you are using. So that you should have really pretty good sample. So you will say, what is the typical size? We are talking of at least 1 million or more. Okay, 1 million event for each of the type. Of course, if the complexity of the problem is higher, this also you need to increase the data sample size. So yes, so overtraining, undertraining are very important to test and validate it before you are ready. So once you are done and satisfied with this, then your network is ready to be applied to the real data, real experimental data. Right now, I look at the mock data, the so-called the Monte Carlo simulated data. I'm confident that my network is reproducible, is giving the desired result as expected. Now you are ready to apply to the experimental data.
So there is a question in the chat box from Arvind. Slide 7, please describe scatter plot, outer scatter dots.
Yeah, can we go there?
Arvind sir, Arvind, if you are there, you can please specify the question a bit. Arvind, are you there?
Yeah. So what was the point, Nisa? If you can just repeat the question once again.
Please describe scatter plot. So I'm not getting
Yes. So
what.
this is just
Yeah.
like you have yeah. So scatter plot by definition is like you have two sort of two variable, two kind of input variable, and I'm plotting one against the other. Okay, one against the other, and that's what we call it scatter plot. But the point is, what you see in this red versus blue, so that's the data distribution, and the point I was trying to say that you have sort of two classes of event in this data, and that you want to separate. And in these two x and y feature variable or input variable, and so if you sort of given the data, you project to x, you get some distribution, or you project to y, you get some distribution, and you see there is this kind of overlapping region, and then you try to optimize. I'm sorry, you want to optimally combine the information, and that's what is done in the multivariate method, machine learning method.
Good afternoon, sir. Sir, sorry, there was an internet issue. Sir, actually, I want to know there was outer dots inside the scatter plot.
Mm-hmm.
Sir, actually, for sir a histogram plot, it's clear to analyze the data.
Mm-hmm.
But sir, in the scatter plot, there is an outer dot. What it means, sir? How could we analyze the data using the
Outer,
scattering?
can you be a little more specific? What do you mean by outer dot? I didn't catch that.
Sir,
Maybe.
there is a density like
Ah.
blue dots and red dot. There is a density, but the outer side of the uh, scattering, there is a single dots and outer two
Mm-hmm.
dots like that.
Right. So those are basically, if you look at see, if there is a region, you can see where the word B is written, or where the word A is written, for example. So if you have data events close to that, those are basically in the histogram projection, like when you are projecting the data into that particular dimension, those are the tail of the distribution, right? So I mean, so the one to the rightmost of the blue histogram, or let's say, yeah, or the leftmost tail of the red distribution, like those are kind of well separated region, right? So if, and the what is important is that, imagine the case if the red density distribution and blue density distribution, they would have been amply separated without any overlap, we wouldn't have been talking about this. So you just put a kind of say these are blue, like this is in classical way when we say red ball versus blue ball, right? So the fact is, the crux of the problem lies that there is a overlap, and that how optimally you want to reduce the overlap. That is what we are talking about.
Any other questions from the participants?
Yeah. Good afternoon, sir.
Good afternoon.
Sir, I am a learner in machine learning, so to say.
Sure.
I have a question. We often encounter about the problem of overfitting and underfitting of data,
Right.
especially usually in cases like support vector machines and all. I'm sorry to raise the topic, which is beyond the scope. There are many different algorithms, but we often encounter like the question of overfitting and underfitting.
Correct.
And today, in the course of discussion a while ago, you said about overtraining and undertraining of data.
Mm-hmm.
So undertraining and overtraining, that is one thing, and overfitting and underfitting of data, are
Mm-hmm.
they related somewhere? And
Yeah.
where do we draw the line that this far is this much is enough, or I'm to say there is we come to an understanding that this much of training is enough or this much of fitment is enough. Is there any standard thing, or it differs from, say, organization to organization, or say people conducting the experiments, like they're the ones who decide the dividing line? Am I articulate enough, sir, in my question? Did you understand it?
Sir, you are not audible, Mohanty.
I'm sorry. I started speaking, but I had muted myself. Am I audible now?
Yeah, sir. Yes,
Yes,
sir, I
sir.
can hear you.
Okay, right. So now you are sufficiently articulate, so don't worry about that. I got the question, so I'll address it. Um, the part I said so far is called classification. The part that you are talking of is what the other thing which I didn't talk of, is a regression. So you're given the data, and now it's not more classifying the thing, right? A versus B. You want to optimally describe the distribution. It could be like Y versus X, like if you are pretty much all of you have done this fitting method, fitting in any kind of fitting, we do chi-square.
Yes, sir. Optimization is the word.
Right. Right. So now the thing is you are doing this in a machine learning method, that how do I do the regression? Like, I want to get the optimal feature, optimal sort of description of my this distribution of something versus something else, expressing Y versus X. So Y equal to fx, and I want to find out the fx form, basically in using the machine learning method. And so then what you do, you have the distribution. So there are three things. There is why you call it variance, and then we call it bias. So the thing is, if you are doing underfitting, so let's say your distribution is something like, actually, in order to make this point clear, I maybe will send some slide, because it's not that I'm not able to share my screen. Otherwise, I'd have shown something. But let's think of the data are distributed in some sinusoidal, a sine wave kind of thing. Okay, so think of like this, or this way. Now, I want to get that feature, the correct feature. If I fit to a straight line, think of like this. You have a sinusoidal distribution, something versus something, and there is a sinusoidal. And if I fit a straight line, this is definitely underfitting, substantially underfitting. There is a large bias. Your fitting, the so-called fit function, whatever you are using, has only gone through maybe couple of data points. That is the point you have zero bias. Rest, some of the thing, if I'm doing the thing, that will be largely biased. So that is really underfitting. Overfitting, the one is the when I'm doing a functional thing, and see, there is, I said this is sinusoidally distributed, but there is a scatter off in each of the average, like each of the slice you take, there is average data point. Now I don't get to the sinusoidal. I look at each of the feature, and then I want to optimize on that. Okay, so in that case, your bias will be exactly zero. Like if I want the fit function touching each data point, the bias is obviously zero. But what you will get, your variance will be large. What do you mean by variance? I said the repeatability and reproducibility. You have really overfit your data, in the sense that you have ensured, that my bias is zero. Like everything, I am able to get the thing correctly. Now problem is, you change the data, you someone else does the thing, you will see you will not get back what you got there. So you, in the whole process, whatever you have done, you have overfit your data, and it's not really correct thing to do. What you want to get is really average, the one which is stable enough. So you can see there is a sort of two opposite trend between the bias and the variance, right? What you want.
Sir, this will be based on some kind of previous knowledge, though we are previous knowledge of understanding, like the optimal value. What you said, it should be something realistic.
Yeah. So we have supervised. This is also supervised way we can do it. Well, I mean, from the data itself, we learn it, and then, so actually, when I express the entire, my final metric, if I express, metric means the quantification thing, so there will be an inherent intrinsic statistical uncertainty that I cannot do anymore. That I cannot do any further change on that. Plus, there is a contribution to your thing coming from bias. There is a third part coming from the variance. The first part, you cannot do anything. So all that I am saying, it is about the regression method, not classification. I wanted to keep my thing into the classification thing, but the question that you are asking about the regression, so so it is more between the bias and the variance part. Actually, it's good point, and I didn't anticipate that I want to go further down there. Although Sunil had said I wanted to not
No,
go
sir.
forward on time.
Thank you very much, sir. You have introduced a new area of learning for me, like bias versus variance. I heard it that those two are very important concepts as well in machine learning. Thank you very much, sir. Thank you very much. I am finished.
Yeah, so if needed, I can, I don't know, Sunil and Nisha, if it is possible, I can try to give some reading material, like some of the slides I can extract, and those things can be, if there is a web page or something, or at least if there is a email mailing list, I can share. Okay.
Yeah, sir, you can share with us the material, and we have a website actually where we are sharing with the candidates.
So probably the thing is, sorry.
Sorry, there was a phone call. Is there anything else anyone want to ask?
Excuse me, sir.
Yeah.
So I need to know about the software which, I mean, like if I need to do a research, the qualitative one, like I do have the ordinal data, which, I mean, like how much is the minimum sample size we should look for to have?
Right. So that
Otherwise, I'm doing a research on the green supply chain management, right? And I need to get the data from the manufacturing sector.
Right.
So what is the what is the sample size I should look for? Although I have calculated, but that is a huge one. So what is the, I mean, like optimal one I can have to work on to get the right result, or the result which can, I mean, like which can I can say that is the right one to get the result from it, right?
I got your question. So you were saying, yeah. So what you need to be assured about, that what is the desired level of error that you can accommodate, or you can sort of say, this is acceptable.
Yeah. That is acceptable. What is the acceptable error I can accumulate? Because I have collected the data in that the chi-square value is coming very large. So
Right. So once you know that what is the desired, I mean, you as a, I mean, you're doing a quality control exercise or something, like you want to say that this is the, I can accommodate, I can withstand up to this level of error in my classification, or error in whatever we said in the bias variance in the regression thing. Then from that, I can actually tell you, there is a, again, I didn't get to that thing. So there is an expression, there is a functional dependence, that in order to achieve, in order to get down this level of error in classification, or error in my, multidimensional optimization scheme, the data size should be this roughly. So I was saying that million, the number I uttered, million, that's kind of acceptance. Is 10 to the power minus 4 or something. That is so I need to get back, and so there is a function, that there is a kind of sort of connection or dependence between the error versus
the sorry to interrupt you. Do we have some research paper which we can quote, like to get some this thing, some transformation to be done to get the data for the analysis, right?
Yeah, yeah. There is many research papers. So there is one book I use. It's actually yeah. So this is a book called Pattern Recognition and Machine Learning by Christopher M. Bishop. So this is a basically sort of information science and statistics book. And all that I'm talking about, see, I didn't get into the mathematical detail, underlying mathematical detail of the scheme, and all these aspects are encoded in this book. I mean, this is one of the book there, but there could be many. Um, so yes, so your question was, can there is any connection between the kind of label to which I want to get to in terms of sort of error in your method or optimization scheme that you can accommodate versus the sample size to be used in the training or in the total sample size? Answer is yes. If that is the question, the answer is yes. And
Sir, may I have the name of the book so that I can get it online or somewhere from the market or any of the library?
yeah, it is. Yeah, right. Pattern recognition and machine learning. Pattern recognition and machine learning. Again, if needed, I can mail in. So, Sunil, Nisha, if you can have the email address of the people attending, then the slides and the reference also.
Yes, sir. We are sharing all the material to them. So you just have to, mail it to Arvind sir or Sunil sir, and then everything will be shared to all the participants.
Sure.
Yes, sir.
Yeah, we will send it to them by email also, or we will be putting this on our website, departmental website as well, so that they can have a look into all of the participants. Yeah, thank you.
Yeah.
Yes, sir.
Welcome.
So anything else from anyone?
No, I would like to thank Gagan for sparing his time and see, I have known Gagan since the last, I think, 20 years or so, and seen him as a very intelligent, hardworking, sincere, consistent, and yet very humble and down to earth. So I think many students and colleagues, including myself, have been motivated by his passion towards his work. So thank you so much, Gagan.
Yeah, I mean, I would have loved to come physically to Jalandhar, but maybe opportunity will come. And
yeah. So it is due from your side. Your visit is due.
So
I think it will take another year to think.
Yeah, getting
things to get normal. Yeah.
Yeah. So yeah. So is there anything else we want to?
I think Nisha, we can. Yeah.
Yeah, just we'll close the session, sir.
Right.
Thank you so much, sir, for sparing time from your busy schedule to share your valuable knowledge with us. The best and beautiful things in the world cannot be seen or even touched. They must be felt by heart. So, I invite Dr. Arvind Kumar, coordinator of this workshop, to give a vote of thanks.
Yeah. Good afternoon, everyone. Am I audible?
Yes, sir.
Okay. Yeah. Good afternoon, everyone. I, Arvind Kumar, as a convener of this workshop, and also on behalf of my colleagues and coordinators of this workshop, Dr. Harleen Dhaiya and Dr. Sunil Dutt, welcome you all in this valedictory function of the workshop. We are thankful to Professor Gagan Mohanty for your talk in this workshop and also for staying with us in this valedictory function. We welcome you, sir, as a chief guest of this ceremony. We are humbly thankful to the Director of NIT Jalandhar as well as Dean Research and Consultancy, the Registrar and Head of Department of Physics for providing us administrative support in organizing this workshop. I am personally very thankful to the Department of Science and Technology, Government of India for funding the research project Fluctuations and Correlations, a hunt to QCD critical endpoint under co-research grant scheme. This workshop is basically funded under this project under the head Scientific Social Responsibilities. And we are thankful to our experts, Professor Kazari Majumdar from TFI Mumbai, who delivered the talk in the very first day of this workshop. Then Professor Raghunath Sau from IIT Indore, Professor Aruna Naik from IOP Bhubaneswar, and Professor Gagan Mohanty today from TFR Mumbai for delivering the lectures in this workshop and enlightening us with their wisdom. We are especially thankful to Professor Raghunath Sahu, who right from beginning, when we thought to organize this workshop, has given us his valuable suggestions whenever we approached him. We are very thankful to him. We are also very thankful to all the participants who attended this workshop and made this event very fruitful through their interactions with the experts. I am sure whatever we have learned during these all 5 days, that will be very useful for all of us in our teaching and research career in near future. And finally, I am very thankful to all the research scholar of our Department of Physics at NIT Jalandhar. They all have worked hard in organizing this event. So we are looking forward again in the future to organize such kind of workshops and interactions. So I once again thank you all. Thank you very much. Nisha, you can proceed further.
Yes, sir. I, Nisha Chahal, regard this as an honor and privilege to extend a vote of thanks at the closing ceremony of 5-day workshop on statistical techniques for data analysis. A very special thanks to our chief guest of the day, Professor Gagan Mohanty. Thank you so much, sir, for joining us. Once a great man said, feeling gratitude and not expressing it is like wrapping a present and not giving it. Today, I take this opportunity to put all my gratitude in the form of words. Thank you to all the dignitaries for delivering the profound ideas with us. A heartfelt gratitude to the Honorable Director, Registrar, and Dean Research and Consultancy, NIT Jalandhar, for always being a motivating force and logistic support for organizing such workshops. Lastly, I would like to thank all the participants for their patience in making this course a success. Once again, thank you to one and all. We hope to see you at some point of time at different forums. Have a good day. Once again, thank you so much, sir.
Just a minute, sir. Professor Gagan, we would like, please give your some of the suggestions or views to the students so that will be very useful for them.
No, I think all I can say that as Harleen said, in life, I mean, you should have some sense. I mean, what you want to achieve in your life, and this is more for the student, obviously, and. If you, and this is something my teacher said when I was a student, if you want to achieve, if you set your sight here, if you don't achieve there, you will at least get here. But if you, so therefore it is very important to keep your sight where you want to achieve. And that should be as high as possible. And just, keeping the thing there will not make you, as in Sanskrit they say, like if the lion is sleeping, the deer will never come and just get into the mouth of the lion, and you must work hard towards that, and you will definitely achieve. So one is the in your mind keeping that, thinking that this is what I want to get into, and then working towards it. These are the two things, and nothing will stop you achieving what you want. So that's all.
Thank you, sir. Okay, thank you all.
Thank you, sir. Thank you so much for your kind words and this motivation.
So I think we can break for lunch now.
Yeah.
Yes, okay.
Thank you, sir.
Thank you for joining. Thank you all the participants.
Your lunch is also due with us.
Yes, sure. And for Punjab, I never, I mean, I don't want to say. Food, my best food. I mean, always.
Yeah.
Right.
So,
Okay.
okay, then have a good day, everyone.
Yeah. Bye.
Thank you. Bye.
Yeah, so for the participants, we will be sharing the feedback link on the WhatsApp groups, and once you fill all the information, and within next couple of days, we will also send you all your certificates. Okay, so thank you very much for joining. Thank you.
Thank you, sir. Thank you, sir. Thank you, sir. Thank you very much, sir.